Okay, hi everyone, welcome back. Hope everyone had a good weekend. Okay. Yes, someone, let me let some people in real quick, Barbara, and I'll answer your question. Or at least attempt to answer it. Okay, Barbara, you said you had a question about a neon sign and how it works. Go right ahead.
There is just a question for the practice problem that I could not understand. They explained it. They say like briefly explained how neon sight works, but I could not understand it.
Okay. Let me see what I can do. Well, first thing we got to remember is when we talked about the energy levels of the electrons, okay? And so there are 7 energy levels to refresh your memory. And then within those energy levels, there are sublevels that we call orbits. Now, these electrons exist in these orbits at a very specific energy level. And what can happen is these electrons can get excited by when they absorb energy, they will go up to the next energy level. They'll go into what we call the excited state. Okay. Now, it's not going to arbitrarily go to any particular state. It's going to go to the next energy level for that particular atom. And it could be in neon gases that have a variety of different material in there to give you the different colors. Now, what happens is as the material gets excited, they go up to the next energy level. And one of the laws of physics chemistry is the conservation of energy and the conservation of matter, meaning that we don't create energy, we don't create matter, we just move things around. And so with respect to energy, if I were to absorb, I use me as an example as an atom. If I were to absorb, say, 10 or 100 units of energy to go to the excited state, I would hang up there for a time period in the excited state, and it varies from atom to atom. But eventually, I will have to drop back down to what's called the ground state where it began. Now, if I go up 100 units of energy, when I come back down, I must release 100 units of energy. Now, I can release this energy in one or a couple of ways. One, I can release that energy as light, and hence you'll see light that is emitted from the material. And so, or I can lose some of that energy as heat, or a combination of light and heat. A lot of the light bulbs, any light bulb actually, even the LEDs, though they may be low on heat, they give off light, but there's some energy that goes off in heat. So the fluorescent bulbs, as you see a fluorescent light, and it's shining whatever color it's shining, and what you're seeing in there is whatever material they use inside the bulb, because it's under vacuum and there's electricity running through it, it will emit that energy back. When it will emit that energy compared comparable to the amount of energy it absorbed, and that energy could be of a specific wavelength, light at a specific wavelength, and you see a different color. So what you're seeing is just excitation of the matter that's inside the fluorescent tube, or in this case, neon. Fluorescent tubes work the same way. Everything, in fact, what we're looking at right now, your screen, is very similar. The molecules on the screen are absorbing energy, and then they emit it back to, as they go back to the ground state, they emit that energy as light. We're able to, a lot more complicated than that as far as the graphics and so forth, but that's what we're seeing. It's just the emission of the energy that molecule absorbed back to the ground state and then giving it off as light. Okay. And you can see if you have an electrical stove, the same thing's happening there. However, a different type of electromagnetic radiation is given off. If you turn your electric stove on and the coil gets warm, right? Because current runs through that coil, exciting the molecules of the metal in that coil. They got to go back down to its ground state once they're excited. But in that case, they will emit electromagnetic radiation as infrared and heat, give out that energy absorbed, and hence your coil gets hot. Okay. So I hope that does help you a little bit, Barbara.
Yes, yes. I have another question, if I
Sure.
may.
Sure.
Is about the periodic table.
Huh?
Question 12, they say draw Lewis dot structure. I
Yes.
didn't understood that. Electron dot formula.
Right. We're going to talk about that and how to make Lewis dot structures. It's basically for an atom, very straightforward, is you find the atom's position in the periodic table, find what group number, and again, this only works for those atoms in the A, the main group elements. And that tells you how many valence electrons. So if you take sodium, for example, it's in group 1A. That tells you it has one valence electron. So you would draw sodium, the symbol Na, and then make one dot. And that one dot represents the number of valence electrons. If you look at, let's say, fluorine, fluorine is in group 7. That means there's 7 valence electrons, and therefore the Lewis dot structure for fluorine will be 7 dots around the symbol F. And that would be true for everybody in group 7, okay? Anybody in group 4 will have 4 valence electrons, so it's a matter of just drawing the symbol and then 4 dots around the element symbol for a Lewis dot. Now, when we get to actual compounds, which we will, a little bit more work will be involved into putting compounds together with their Lewis dot structure for compounds. But for atoms, simple, how many valence electrons, that represents how many dots. Okay. We'll get to that. All right. Any other questions? You're welcome. Any other questions? No, because what we're going to do is we're going to get into what is called chemical bonding. Now, think about this for a moment. There are, who knows how many chemicals are out there? Just tons of them, different types and different things. We're not out in the world, and even in our body. Of all these chemicals there, we only have 2 types of chemical bonding. Now, when we talk about chemical bonding, there's really, like I stated, 2 types of chemical bonding. And one type you can be thought of is, say, 2 magnets, okay, where they attract each other. And I got 2 magnets here, and they come together, and they just make this attraction. Now, we've been talking about these valence electrons, and we said, well, depending on the group that they're in, the element that is, we can determine how many, well, let me restate this. I'll make sure we get this correct. We talked about metals and nonmetals, and I stated metals want to lose electrons. And we also talked about nonmetals that want to gain electrons. The driving force is to get 8 valence electrons around the valence shell, the outermost shell. Now, when that happens, either losing or gaining electrons, we make ions, okay? And these ions will either have a positive charge and a negative charge. And when we get ions that come together, where am I? Somebody's, give me 1 second. Okay, when we have ions that come together, think of it as 2 magnets coming together. We got a positive ion together with a negative ion coming together to form a partnership, if you will, to form a compound, because we've got two different elements. They don't make a bond, they make an attraction to each other because of the full charge of positive and negative charge, okay? That is one type of chemical bond, which has a specific name. We call that ionic, okay? And there's, I'll have more to say about that in a second. The other type of bond, which is what we call a covalent bond, think of the word co, they're like coexisting, valent, talking in terms with respect to the valence electrons, that the atoms come together to form a physical bond. And my fingers represent a bond where they overlap and they come together and they start and they share those electrons in that bond. Now, the other aspect to remember that every bond, there's three types of bonds for these type of covalent bonds: single, double, and triple. Okay, single, double, and triple. Every bond has two electrons that are shared. They're not separated like the ionic bonds where you just attracted together like magnets. Electrostatic attraction is what it's called. But the covalent bonds are actually shared between the two atoms. Now, this sharing is either equal sharing or unequal sharing, which is related to the electronegativity. Remember electronegativity? We talked about it. That is the measure of the affinity of electrons being pulled onto themselves, with fluorine being the most electronegative element, right? And so if fluorine was in a covalent bond, the most electronegative element there, it would tend to pull all those electrons toward itself. And so the result is we have a specific type of covalent bond, which we call polar. And then if they share equally, we have another type of covalent bond, which we call nonpolar. So quickly, we have ionic bond, like two magnets come together, covalent bond, which are two electrons for right now, sharing a bond. And then underneath the covalent bond, we have either equal sharing or non-equal sharing, which results in something that's polar or nonpolar, which affects the properties of that chemical. Okay, that's why, for example, like dissolves like. Put this in your your long-term memory. Like dissolves like. If, for example, okay, I grew up with 5 sisters, and in the evenings, it was like Halloween. Why do I say that? Because they were putting stuff on their face to remove all the makeup they used during the day. Now, soap and water doesn't very effectively for them at that time. I'm told now the makeup's all changed, obviously. Soap and water didn't work for a while. So they needed some oil-based makeup remover, okay? Because that oil base had what we call a non-polar property. Water has a polar property, so water wouldn't work very well. So they use some, I don't know, 1030 weight oil to get this stuff off. This is not polar, but much more on that later on. We'll talk about that. And all of this is related to those crazy electrons, okay? All right, so don't forget the shapes table. Make sure you got one, readily available, because we're going to use that. Because we're going to be able to now start, when we talk about these bonds, we're going to start putting them together. And even more so than that, once we put these two elements together or more, we can start determining the shapes of these compounds and what shapes they exist, what shape they have in nature. Okay. Now, as I stated, atoms want to be like noble gases because that is a very stable state. Okay. Having the outermost shell full, having the electron configuration S2, P2, P6 full, 8 valence electrons. Be it on the second energy level, third, fourth, etc. Obviously, it's not in the first, because the first energy level only has the S orbits. The second has the S and the P, and that's where the P's come in. But for those elements in the first energy level, their goal is to have the S2 configuration, like helium. Helium has 2 electrons, and its orbit is full. It's S orbit in the first energy level. Okay, so that's the octet rule. Okay, we talked about metals. All metals And we have a periodic table to show which of the elements are color-coded to tell you which of the elements are metals, okay? Literally everything to the left of that little stair step on the periodic table is a metal, with the exception of hydrogen. Remember that, don't put hydrogen under the metal category, even though it's to the far left of the periodic table. Hydrogen's there because it only has one valence electron. And remember, it's in group 1A because everybody in group 1A has one valence electron. So, but hydrogen is not a metal. When they lose metals, they become what are called an ion, but more specifically, a cation, C-A-T-I-O-N-S. Non-metals gain electrons, and they have their own name. All the negative ions are called anions. Now, here's your first type of chemical bond, which is an ionic bond producing an ionic compound. That is a combination of a metal and a non-metal. Let me repeat that. Let me highlight that. Okay, get the right color here. Combination of a metal and a non-metal produce an ionic compound. Okay, for example, we have something like what you put on your French fries. Where's my, uh-oh, I lost my, give me 1 second, my wand, my pen is not functioning for some reason. All right. Maybe it is now. Yep. Okay. For example, something we put on French fries, right? We're all familiar with sodium chloride. Sodium is a metal. Chloride is a non-metal. Hence, what we have, sodium chloride represents an ionic bond, therefore an ionic compound. So any combination of a metal and a non-metal is an ionic bond or ionic compound. And the result is very similar to two magnets coming together, as I stated, because on one hand, when sodium becomes ion, remember that sodium is in group 1, and when it becomes ionic, it loses 1 electron, so it has a full positive charge in it. Chlorine, I said chlorine because that's the element, has 7 valence electrons. It's a non-metal. It's going to gain 1 electron to give us a -1 charge. And so the ions, sodium ion and chloride, and remember we changed the name now to chloride, from chlorine to chloride when it becomes an anion. Those two come together, okay, like two magnets to form what's called an electrostatic attraction. They're not sharing any electrons, okay? No sharing of electrons involved here. Okay. Main point, metal and non-metal. So it's important that you recognize who's a metal and who's a non-metal so you can classify what type of compound. In general, ionic compounds are very soluble in water. Sodium chloride we know is soluble in water because they are ionic, okay? We're going to learn there's different degrees of solubility, but that's further down the road. So ionic compounds in general are soluble in water. Okay. So when we start putting compounds together, we first create the ion. And then keep it in mind that we have to partner up a negative and a positive. And so the question here is the calcium ion, who would be a good partner for the calcium ion? Well, obviously it can't be the lithium ion, right? Because the lithium ion is a positive charge. Positive and positives do not attract. Negatives and negatives do not attract, okay? It's only a positive and negative combination. Okay. You don't believe me? Try to jump start your battery, and you put the cable in the wrong pole. You're gonna get a little spark going on. Okay. Same thing is true. Think of it as two magnets, two magnet bars that are magnetic. You try to put the negative, the North Pole and the North Pole together, they won't. They repel each other. As the same with the South Pole and the South Pole, they repel each other. But the North and the South attract to each other. Okay. So think of that for the ionic compounds. And some examples, I use sodium chloride as one, but we got potassium chloride, we got calcium bromide. You're at the point, you got a couple hundred compounds you can put together. All the metals in group 1, all the metals in group 2, those are ions that you can combine with the anions of all the nonmetals, the fluorine, the chlorine, the bromine, the iodine, the oxide, the sulfide, the nitride, all those combinations thereof, you can mix and match. I wrote down sodium chloride, but here you got potassium chloride. You could use lithium chloride. Okay, you see how we're building up our library of names of compounds. Okay, now, when you have nonmetals come together, okay, you have what are called covalent bonds, or which in essence are covalent compounds, okay? Nonmetals. And that's the key part right here, this statement right there. Non-metal combination. Remember, we're making compounds. Compounds is any combination of two different elements. If those two different elements, so one of them is a metal, one is a non-metal, you have an ionic compound. If both of them are nonmetals, you have a covalent compound. And in that case, they're sharing a bond. Okay, they're sharing electrons. Okay, things like H2O, okay, hydrogen and carbon dioxide, CO2. Carbon and oxygen are both nonmetals, right? Okay, hydrogen and oxygen are both nonmetals. Those are examples of covalent compounds. And what do I mean by sharing? What do we do? Well, let me draw the structure of water, for example. Water consists of oxygen, and then bonded to the central atom of oxygen are two hydrogens. And we draw a line here, okay? Single line. That single line represents two electrons. Let me clear it up a little bit. Now, I'm going to draw it two ways so you can see they're both the same thing and just different ways of drawing. Okay. I can draw a line on the left side between oxygen and hydrogen. That line represents two electrons. It's the same thing if I were to draw two dots. Two dots, each dot represents an electron, okay? Now, I can sit here and draw dots all day long. However, that's a lot of dots. So what we do is we simply draw a line, and that line represents two electrons. And that single line represents what we call a single bond. So a single line is a single bond. Okay, we can do a double line like the equal sign, for example, and that is a double bond. Okay, again, each line represents two electrons. And we also have one that has three lines, and that is a triple bond. Again, each line represents two electrons. So a triple bond has a total of 6 electrons. A double bond has a total of 4 electrons. Okay, we got 6 electrons. I'm drawing that 6E with a hyphen, 6, and 4 electrons here, and 2 electrons here. And those electrons are being shared by the two atoms at the end of these, at the either side of the bond. Okay, and that sharing, like I stated, could be equal sharing or unequal sharing. But more on that. down the road. And so, like I stated, we can do double dots or we can do the line to represent a bond. So we have carbon dioxide, water. Those are some examples. There's, a large number of them. And if you look at the nonmetals that are involved in chemistry, there's not that many, but yet there's so vast combinations of them out in nature all around us. It's just amazing of the different combinations you could come up with. Okay. Now we're going to talk about ionic formulas. And I just stated earlier that ionic formulas is a metal and non-metal. Now, in order to put them together properly, we first need to write them in the form of the ion that they would have, okay? Because when we put them together, we have to put them together such that the negatives cancel out the positive, or the vice versa, whichever you want to call it. So I got to have enough negatives and enough positive ions together that when you put them together, they cancel each other out to give us a net zero for that compound. So why is the formula CaBr2 is the question, okay? Someone had a question. Sorry, I just saw the chat here. What? My dad's up there somewhere laughing. Okay. Don't quite get it, but all right. Gains, Skylar, you said calcium gains 2 and bromine loses 1. Not quite. Calcium is a metal or a non-metal? Okay. Find calcium in the periodic table. It should be in group 2. It is element number 20. Okay. So by its position on the periodic table, what can we say about calcium? Is it with respect to it being a metal or a non-metal? Which one would it be? You can tell me that. Oh, got 2 messages here. Metal, that is correct. Calcium is a metal, and therefore calcium will lose electrons. So the next question will be, well, how many does it lose? Well, then to answer that, we determine its group that it's in. Remember the group numbers, Roman numerals 1 through 8 for the main metals. Okay, the A's, it's in group 2. So that tells you that calcium, of those 20 electrons that calcium has, 2 of them are in the outermost shell. Even specifically, those 2 are in the 4s2 energy level and orbit, 4s2 orbital, okay? And being a metal, it's going to lose those 2 electrons. That being said, when it becomes ionic, calcium will have a +2 charge, okay? When it's ionic, when it's an ion, specifically a cation. Now let's take a look at the way it's written, the Br. We first got to determine Br, is it a metal or non-metal? Well, we know its position is in the far right of the periodic table. So that right there should tell you it's a non-metal, okay? Specifically, it is element number 35. It's in group 7. Being in group 7, and being a non-metal, it will gain an electron, specifically gain 1 electron, because gaining 1 electron makes it a negative ion, because it's non-metal, okay? And it has 7 valence electrons as bromine, which means it has room for 1 more. Remember, the driving force is to become an octet, and it gains 1 electron. Calcium, by losing 2 electrons, now is isoelectronic to argon. It has same number of electrons as argon, okay? Remember, that's the driving force. Bromine now has the same number of electrons as krypton, the noble gas in front of it. And so now it becomes a negative ion or anion when it becomes ionic. And we got to put these two together. Now we got to put them together such that I need two negatives. So I put a 2 in front of the bromide to cancel out the +2 of the calcium. So that +2 becomes the subscript in bromide. Okay. I repeat that. That's that 2 sitting right there in front of the bromide becomes the subscript. This 2 right here becomes the subscript for the bromide, which tells you that calcium has 2 bromides attached to it. Calcium is the central atom here. Now, the thing about ionic compounds is this. The metal, as far as the formula, the metal is always written first. And 99.9999% of the time, I don't say 100 because always, I'm sure some exception that pops up, but 99.9999, etc. The calcium is the central atom, and everything else that follows that is bonded to the central atom. In this case, calcium. Okay. All right. Let me clear this up a little bit. All right, so we've got to put them together. So once we put them in ions first, and this is the deal that you really have to do first all the time, because later down the road, you may be given the word calcium bromide. And to write the formula for any type of reaction calcium bromide might be doing, you have to write the formula for it, right? And to write the formula, you first put them in ionic form such that you know how many of each to put together so they cancel each other out. With time, obviously you learn that it's CaBr2, but in the beginning, you get into the routine of breaking them down into ions and then putting them together with the correct number of subscripts. That subscript from the bromide is etched in stone now. We don't change that. You put it together in the correct ratio, and that's the way it is. That is the formula for calcium bromide. Okay. If we need to add more calcium bromides or show that we have more of those, we put the coefficient, and we can say maybe, for example, 3 calcium bromides. So we put a 3 in front of the whole formula. Okay, calcium or 4, whatever number you need. That's the coefficient. Okay. Now you might be thinking, all right, wait a minute. We talked about diatomic the elements. We have no fear of icicle beverage. Remember those? Okay, so you might be looking at that formula, CaBr2, and think, oh, bromine, diatomic. But here's the difference. Right immediately in front of this is calcium. So that would tell you that, you are dealing with ionic compounds versus diatomic bromine element. Okay, note the difference. There's nothing in front of Br2 here that I wrote. That is bromine. To the left of the verses there is calcium bromide. Calcium bromide. Okay. Now somebody asked me, well, could I write it like this? Okay, technically you're not incorrect. By convention, it's written with the metal first. Okay. And then followed by whatever follows. So you write that first, the metal, and then generally the non-metal. Okay, let's continue. So let's take a look at these compounds here. And the question says, and it's an exercise here to determine which of these. Now, obviously, we don't know what they are at this point in time, and that's okay. But I'm hoping that you can recognize the elements involved in that compound and determine whether it's metal or non-metal. And from that information, determine if it's ionic or not, okay? And so let's take a look at the first one. We have K and Br. And we have, so that means let's get the names on them so we can start practicing. Okay. Anybody want to name that first one? Potassium bromide. That is correct. And so is the first one. Now, next question would be, is potassium bromide ionic? It would be yes or no. And that is correct, Haley. It is ionic, and we know it's ionic because we know the potassium is a metal, and we know the bromide is a nonmetal. Hence, we have a ionic compound. Okay. Let's take a look at the next one. It's called SO3. And if you ever drove in front of a car emitting a lot of fumes, you probably, that is correct, Caitlin. That is sulfur trioxide, the name there. And that's an exhaust on some of the engines. You have a rotten egg smell in front of the car. That's what you're smelling. It's a nasty gas that comes out, and what happens, it gets up in the atmosphere, reacts with water, you form sulfuric acid, which is pretty acidic, and then it rains and it comes back down on Earth, and then it just causes all kinds of havoc on stone, for example. There's a lot of stone back east, old stones that are kind of worn down due to the acidic rain that drops. And then what happens, it changes the pH of the soil, which causes a lot of heavy metals to get dissolved and get in our water system and then cause problems. So a lot of problems. Now, sorry for the side note. So that is correct. The name of that is sulfur trioxide. Now, we are just beginning to, talk about the names. Now, sulfur can be spelled SULPHUR, that's fine, or the FUR. Okay. And notice we use the prefix trioxide. Compared to what we did earlier, that we talked about the calcium bromide, we called it calcium bromide and not calcium dibromide. Now, with respect to naming, put this in long-term memory. Ionic compounds, we don't use prefixes like tri, tetra, penta, whatever, okay? It's simply what it is, potassium or calcium bromide, or any, like down at the bottom is magnesium chloride, not magnesium dichloride. However, for covalent compounds, yes, we do use prefixes, and we'll have more on that. So hence, this is why it's sulfur trioxide, because one is it's non-metal, right? Sulfur and oxygen are both non-metals. Therefore, it's a covalent compound, okay? Therefore, it's not very soluble in water. It doesn't break apart in water. Potassium bromide, being ionic, will dissociate in water and will dissolve in water, okay? So answer here would be no, not ionic. Okay, HCl. Now here's the tricky part. Not real tricky, but a thing to remember. Okay. And it's not written there, but it should be told. I'm going to go ahead and introduce you to it. HCl, first thing you see is the hydrogen in front. Now, 99% of the time out here when we write formulas out, when you see a hydrogen written first, you can assume almost, like I said, 99% of the time, that it is an acid like this one, okay? And we have a multiple acids out there. So this one here is hydrochloric acid. However, what's missing is AQ in parentheses. When it is dissolved in water, an acid is dissolved in water, it is called hydrochloric acid. But it also exists as a gas, which means no water involved. And if it just says the physical state is G in parentheses, and then it's just hydrogen chloride. Now, when those of you taking have taken the nomenclature exam, don't forget about that. This pops up and they do an HQ, meaning aqueous, or they do not. I've been giving you guys credit for it because we really don't talk a lot about this. So whether you name this hydrogen chloride or hydrochloric acid in the nomenclature exam, I definitely will give you credit for it. And the only difference is that HCl in water makes it an acid. HCl out of water in gas just makes it hydrogen chloride. Yeah. Muratic acid, muriatic acid has to do with the concentration. There's up there, I used that a lot back in my construction days. They use muriatic acid, just different concentration. They gave it the name muriatic acid. Okay. All right. It's good for once you lay bricks and block it, and especially brick, and you want to get rid of that white cement discoloration, you wash it in there. And yes, it's used in pools, to do cleaning once you take the pool out. But I think they may use it for adjusting the pH too. Not 100%, but I have not much experience with the pH with the pool as far as upkeep. All right, third one. So it's HCl. Is this ionic? I guess the question is HCl ionic? Exactly, no. Now, you might be tempted, that is correct. It is a covalent compound, and no, it's not ionic. You may be tempted to make it ionic. Why? Because on the periodic table, hydrogen is in the far left side. You might be thinking, honest mistake, it's on the left side, it's a metal. But remember, hydrogen is the only non-metal on the far left of the periodic table. And again, it's there because it has one valence electron. So no, it is not ionic. And yes, it is a covalent compound. And one more bit of information for you with respect to acids. And this is just one of them. We have hydrofluoric acid, we have sulfuric acid, and we'll get to those, and muriatic acid. We even have organic acids. If you like Italian dressing, you're eating acetic acid, or AKA vinegar, okay? These are acids are the only covalent compounds that actually break apart when we put them in water, okay? Ionic compounds, when we put them in water, when I say break apart, they dissociate. It's simply like the two magnets examples I have. Okay, if I have an ionic compound and I place it in water, they will dissociate in water. Now, some dissociate 100%, some dissociate a little bit. And that's not 100%, maybe 5%. But nevertheless, all ionic compounds will dissociate. Covalent compounds do not dissociate when I place them in water, okay? The only exception is acids that are covalent compounds. And because of the acidic nature of the material, they will dissociate to form a hydrogen or an acid proton. We have a whole chapter on that, but just giving you a heads up on that. Okay. Next one, bromine. Notice I said bromine and not bromide, right? Because what do we call this? Is this ionic? The name of this is bromine, and the answer is it's diatomic. And so, yeah, that's correct. It's one of the diatomic elements. So no, it is not ionic, okay? Furthermore, remember earlier I talked to you about covalent bonds, how they share those electrons, and I said there's two types of sharing. There's equal sharing and unequal sharing. Well, this is an example of equal sharing, because I have two bromine elements that are sharing those two electrons between them, okay? And because the electronegativity, remember that thing again, electronegativity, they're both the same. Is like having a rope pulling contest with two people with equal strength, same weight, same strength, and they're pulling at rope equally. Now, if I look at HCl, it's a covalent compound, but I got two different elements. And let's assume now we're not in aqueous solution, but we're in gas, so it's hydrogen chloride. There is a covalent bond between those two, but not equally. Chloride in this state, HCl, will pull these electrons closer to itself, and we create what's called a polar covalent bond, okay? Versus bromine, which is a non-polar covalent bond. All right, what about CO2? We call that, anybody want to give it a name? I'll give you the carbon part. Carbon. What can we call that? CO, okay. Oxide, you're 50% correct. Remember, carbon and oxygen are non-metals. So we use, in non-metals, we use prefixes. So it's dioxide. That is correct. If it was a single oxygen, CO, then guess what? It would be carbon monoxide. You have to name the single, it wouldn't just be called carbon oxide, but it'd be called carbon monoxide to show one oxygen, okay? Now, is this covalent? Excuse me, is this ionic? Is the question, the main question? No, that is correct, Odette. No, it's not ionic, okay? And then finally, the last one, MgCl2. Anybody want to take a shot on the name on that? Magnesium chloride, exactly. Not magnesium dichloride. Sometimes they're tempted to put the di because they see two here, but it's not. Just one because it's ionic. And ionic compounds do not use prefixes. No prefixes. And the question is, well, how do we know that formula is correct? Well, let's double check ourselves. What do we know about magnesium ion? Well, we know magnesium is in group 2, and when it becomes ionic, we'll have a +2 charge, just like calcium did. It's red is right above calcium. Okay, that's what they both remember what they shared when we did calcium earlier. Okay, both of these, magnesium and chloride, have two valence. Excuse me, calcium and magnesium have two valence electrons. The difference is for magnesium, those two valence electrons are in the 3rd energy level for magnesium. For calcium, those two electrons are in the 4th energy level, just a bigger shell, okay? Calcium is a bigger element. So, and both of them being metals are going to lose those 2 electrons to end up with both of them having a +2 charge, okay? All right. And the chlorides, like we did earlier with bromides up here, like this bromide has in group 7. And it will gain 1 electron. I put circles around my charges just to keep track of them for me. A circle around it tells me it's the charge. It's not necessary to do that. It's not a habit in my case. So I got a chloride with a -1 charge. Okay, so that is the ion or the anion of chlorine. Okay, Mg+2 is the cation of magnesium, the magnesium element. Now I got to put them together, and I got to put them together such that the negatives cancel out, which means that I need 2 chlorides for every magnesium ion, and hence the formula is MgCl2. Okay, which is correct the way it was written. Okay. So these, the only 2 are the potassium bromide and the magnesium chloride. Okay. Remember, ionic compounds are the combination of a metal and a non-metal. Now, excuse me, for the bonding itself, so if we take the sodium atom, which has a 1 valence electron, okay, And the color, I guess you call that pink, I guess, dark pink color. You can see the relative size to demonstrate the size of the atom. Well, when it becomes ionic, it loses one electron. And look at what's happened to the diameter of the sodium ion. Definitely got smaller, right here compared to right here, because it lost that one electron. And by losing one electron, now the outermost shell is the next energy level in, because that shell that one electron is empty, so it's no longer there. Physically, with an electron, it's there, but it's empty. Okay. With respect to the chlorine atom, given its relative diameter, it's in group 7 and will pick up an electron. And guess what happens? Picking up an electron, now it has 8 electrons in the outermost shell, and the electrons, being negative charge, will repel each other. So the anion is larger in diameter than the element itself. And so that denotes the attraction here between the sodium ion and the chloride ion, as there were two magnets that come together. Okay, there's no sharing of anything. Both of these, the ion and the chloride, have full valence electrons. The ion, sodium ion, has a full valence electron because now it's isoelectronic with argon. Okay, 10 electrons on the outside, and the chlorine is isoelectron with argon, and 8 electrons on the outside. Okay, and there's no room for sharing. They're just attracting each other because of the charge. Yeah, I just saw your nose color. Yes, that's a good point. Mg and Mn, be careful. They sound very close together name-wise. I see that pop up a lot. Mg is magnesium, and manganese, so is Mn. So yeah, it does happen. All right. Point here, notice the changes of the size. Let me clear them up a little bit. Okay, this is basically what going over what we've hopefully know by now with respect to who's losing ions and why. Sometimes there's a confusion. Well, why did this gain a +2 charge? Why does it have a charge of this amount once it becomes ionic? And why is it a negative charge? And how come it's a -2 versus -1, -3, that kind of scenario? And the thing to remember is the octet is trying to fulfill the octet. And it will these elements will lose and gain whatever number of electrons they need to lose to fulfill the octet. The thing is to remember, this is only true. Well, we can only predict 100% of the time for the A elements. Okay, the D elements. Remember the guys on the inside, the 10 columns. They have a variety of charges that they can exist. We can't predict. It depends on the reaction conditions. But we can predict for group 1 and group 2. Okay, group 1 and group 2 always have a +1 and a +2 respective charge. So magnesium atom had 12 protons, 12 electrons. When it becomes ionic, it's going to lose electrons because it's a metal. Plain and simple, it's a metal. So it would lose 2 electrons and now has 10 electrons, which is isoelectronic with, neon. Had a senior moment there, I had to look it up. Okay, on the other end of the spectrum, you have sulfur that has 16 protons and 16 electrons. Sulfur is in group 6, going to pick 2 electrons. And now it's isoelectronic with argon. Yeah, argon, and have a total of 18 electrons, okay, by gaining 2. Now the question is, well, how does the charge come into play? Now think about this. Just think of it in terms of mathematics, if that helps. Okay, because we know that the protons have a positive charge. And we know that the electrons have a negative charge. So if I have 12 pluses and 10 negatives, well, what's my net? You know, think about that mathematically. I got a +2 net charge. Okay. The sulfide has 16 positives and 18 negatives. So mathematically, it has a net charge of a -2. Okay, so think of it, maybe that helps in terms of mathematics. But also remember that sulfur is a nonmetal, so it's going to gain electrons. I might sound I'm repeating myself, but that's for a reason. Okay. And it might sound redundant at this point, but eventually I won't be saying as much. But these are key aspects of this whole thing, because this is just the beginning of the alphabet. Remember, I talked about the elements, think of them as letters, and then we're going to make some more letters, special letters with losing and gaining electrons. And we're going to put these letters together to make compounds. We started doing that. Now we're going to take those compounds and react them with other compounds to form reactions, to make new products, and so forth. So this is the beginnings of it. All right, so the magnesium ion and the sulfide ion are obviously going to attract each other because of their respective charges, and they have what is called an electrostatic force that brings them together, compared to magnets, where electromagnetic force is bringing them together. Either way, they're being brought together. Okay. All right. So let's recap the ionic size. We know that the cations lost electrons. So by losing electrons now, they have more protons than they do have electrons. So the result is this: not only have they lost electrons, and if those electrons were in the outermost shell, that outermost shell is now empty. And so what's left over are less electrons, but more positives. So that force that attracts the positive protons and the negative electrons pulls them even closer. Okay. And so the diameter of the ion is much smaller than that of the element. Okay. On the other end of the spectrum, we have the anions are now picked up in electrons. So now we got more negative forces going on the orbit. And so they're going to push apart. They're going to repel each other. So the result is the ionic size of the anion is much bigger than the respective element. Okay. All right, some true and false questions regarding ionic bonds. Some metalloids do form bonds, again, because of the character having metal and non-metal characters. They have the capability, depending on the reaction conditions, to actually form bonds. For example, silicon. Silicon can form bonds. Silicon is a metalloid, and it's right below carbon. Okay, so theoretically, carbon is very unique. Carbon has a capability of forming bonds with other carbon atoms, which is a good thing, because without that capability, we wouldn't exist. Not a lot of atoms can do that, where you can create a string of atoms all bonded, to form chains. We have a lot of fatty acids, tissue, so on and so forth, made up of carbon-carbon chains, big long ones and so forth, and short ones. And silicon has that capability too. And so theoretically, you might think about it. I know the old original Star Trek, they kind of touched on it. It was pretty interesting. Have a life in the form based on silicon. So interesting thought. Anyway, yes, so to answer your question, yes, I'm going to bring Star Trek in quite a bit. You might think, oh, this guy's nuts. That's okay. There's a lot of stuff, and when I say Star Trek, I'm talking old school Star Trek, not the next generation. I'm talking about way back Captain Kirk and TV series, because there's a lot of stuff that happened there. Me as a young kid saw this and like, wow, this is cool. You know, if you go look at one of those old Captain Kirk, you'll see the communication officer talking with something in her ear. You know, we do that now. Bluetooth. Okay. All right. Sorry about that. Got a side note. But yes, some metalloids can form bonds, to answer your question. The aluminum atom loses electrons and the iodine atom gains electrons. Do you think that's a true statement or a false statement? That would be true. Okay. Aluminum is a metal, will lose electrons, and iodine is a nonmetal and therefore will gain electrons. And specifically, Skylar, that is correct. It will lose 3 electrons because aluminum happens to be in group 3, meaning there are 3 valence electrons. Okay. And iodine is in group 7, being a nonmetal, it will pick up 1 electron, give you a -1. Now, the aluminum atom is larger in radius than the aluminum ion. Would that be a true statement? That would be, oh, let me let somebody in. That would be a true statement. Okay. Think about this now. Think about it. We said you got to read the question carefully. It says the aluminum atom. Okay, so the aluminum atom has 13 electrons, with 3 of them in the outermost shell, as compared to the aluminum ion, which now is the cation that lost those 3 electrons. Okay, by losing those 3 electrons, it now has more protons and pulls those electrons even further down. All right. The iodine atom is smaller in radius than the iodide ion. Okay, again, read the question carefully. Okay. Would that be a true statement? The atom is smaller than the ion. True? Not true? 50-50 chance. It's smaller. True. And the atom is smaller, remember, because the ion now gain an electron. And so there's 1 more electron in that outermost shell. So and then there's 7 in there already with negative charge. Now we're throwing 1 more with negative charge. They're going to repel. Okay. And get larger in size as far as the radius. Aluminum and the iodide ions form a bond by attraction. And that is a true statement. It's an electrostatic attraction between ionic compounds compared to a covalent compound, covalent bonding with sharing of electrons. Okay.
Professor, I have a question.
Sure, go ahead.
Could you repeat again why number 2, number 3 is true?
Number 3? Okay.
Yes.
All right. So if we look, and let me draw it here maybe. Okay, we have the iodine. I don't want to draw all of these, but the iodine has, and I'm just going to draw the outermost shell. And let's assume that's the outermost shell. And so how many electrons would the iodine atom have in the valence shell? How many would it have? 7, exactly. So I got 1, 2, 3, 4, 5, 6, and 7. Okay, and all right. Maybe I should have drawn it with red. And so that's 1, and that's 2, 3. Well, obviously not the scale, okay? So we have 7 valence electrons on the outermost shell. It's in group 7. And this is the atom. Okay, that's the element. All right. Now, it's a nonmetal, so it has a tendency to gain an electron. Why? Because it's got an empty spot here. It's got room for one more. Okay. And when that happens, it's going to pick up 8 electrons. And now by picking up 8 electrons, I won't draw them on here. I pick up one more electron, I got more negative. So now I have 36. Don't I have 36 electrons? 8 of them in the outermost shell. And so the size gets bigger because there's more negative charge and they repel each other. Okay, does that make sense, Barbara?
Yes, thank you.
Yeah, and then down number 4, this is the true statement here because it's an electrostatic attraction. Electrostatic attraction between the positive charge and the negative charge coming together. Okay. And that's why number 4 is true, because that is how one forms an ionic bond. It's an electrostatic attraction between a metal and a nonmetal, compared to a covalent bond, which is a totally different. We're actually sharing electrons. Okay, not much to say about metal bonding, metallic bonding. Just that there's a whole slew of electrons on the surface of metals, and that's why they're very good conductors of electricity and also very good conductors of heat. Got all these electrons just being shared amongst each other. And that's about much what we're going to really say about metallic bonding. Other than compared to metallica bonding. I don't know if you caught that. Okay, no. All right, so covalent bonding. Now what we're talking about is electrons that are actually being shared. Okay, they're actually being shared here. You know what? It's 2:11. Let us take a quick 15-minute. Okay, let me pause it. Okay, let us continue. Second here. All right, so we were talking about ionic bonds. Now we're going to get into covalent bonds. In this scenario, it consists of sharing electrons between non-metal elements. Now, the non-metals could be different or they could be the same. Okay, but there's actually physically sharing of the electrons forming a bond. We have 3 types of bonds: a single bond, a double bond, and a triple bond, as I stated earlier. And we generally denote those by a line, or we could say 2 dots. Every dot represents 1 electron. So I can either draw a straight line or I can designate it by 2 dots like this. And that represents a single bond. And then we have double bonds, or I can write it with dots. So in this case, I have 4 dots that represent a double bond. And then we have triple bonds. Okay, and I can represent those by dots, which again, we have 6 electrons. Now we're going to see a lot of lines being drawn because you can see here, you can run out of a lot of dots to draw. Now we have models that we utilize, what we call space field models. You can see here, right here, the red represents the oxygen and the dark color represents the carbon. And generally, like I stated again earlier, when we have compounds, like covalent compounds, the first element that is written first, like in this case, carbon in carbon dioxide formula, is the central atom, okay? And anything that follows is bonded around the central atom. It could be bonded singly, double bonded, or even triple bonded, depending on the condition. We're going to learn how to do that, how to determine what type of bond is being created. Except for here in this scenario where we write H2O. By convention, hydrogen, the two hydrogens are written first, and then you got oxygen. But what's happening here, the white color represents the hydrogen, and then we have the oxygen as the central atom, okay? Denoted by the red color, and the two hydrogens are bonded there. Notice there's a specific angle here between the two hydrogens. We're going to learn about that angle and how that works, as there is a specific angle between the carbon and the oxygen, okay? All right, so covalent bonds, as we stated, sharing of electrons. Now, the trouble that sometimes that students have at times is this business of sharing equally or not equally, okay, which is related to the electronegativity. So what I do is I just very generically write a bond in two letters. In this case, I use the letters A and A, which represent two nonmetals. Doesn't make a difference what they are, but they're two nonmetals. The fact that they're the same nonmetals, okay, is what I meant to say, two of the same nonmetals, is that they have the same electronegativity. Therefore, when that bond in here, that bond in the center right there, it is equally shared. It's like that tug of war between two atoms or two people that are equal strength and equal size. That atom is that line, that rope, which is designated by the line, is not going to go anywhere. Okay, so equally shared electrons. If I replace one of those letters with the letter B, now I have a totally different element. And that results in an unequal sharing of that bond, because one of these elements, A or B, is going to have a stronger electronegativity. And having a stronger electronegativity, which is a measure of how the affinity to pull electrons onto itself, that bond will be shifted. The sharing will go to one or the other, okay? That's what you mean by sharing or unequal sharing. That results in a property of that compound or that bond, which makes it either what we call a polar bond or a non-polar bond, which is related to whether it is soluble in a oil-like material or a water-like material, because water is our reference point. It's very, very polar. And like dissolves like is something else that we're to keep in mind. So we're going to have a lot more about that down the road here. But it's important that you understand the difference between the covalent bonding, polar and non-polar, equal sharing versus non-equal sharing. And we'll be able to designate which direction that sharing goes by looking at the electronegativity of that element and see the two elements involved and determine who has a higher electronegativity, using fluorine as our reference point, okay, to help us make the decision. So as I stated, single bonds are two electrons. It's a pair, and they're being shared, be it equal or unequal, okay? And then we double bond 4 electrons, triple bond 6 electrons, okay? The single bonds are the longest with respect to radius between the two. They're the longest and generally the weakest with respect to bond strength. Doesn't take a lot. Let me restate that. The amount of energy to break that bond is less than a triple bond, because the triple bond generally is a shorter bond and generally a stronger bond. Case in point, acetylene. Acetylene gas combined with oxygen as we burn it gives out so much energy that it can cut metal. We're using an acetylene torch to cut metal. As compared to, let's say, butane. Butane is a single bond. Butane is, flick your bic. That's the gas that's in your little lighter, gas lighter. Doesn't give a lot of energy. You couldn't burn metal with a lighter to it, unless it happens to be magnesium metal. That burns different type of metal. But I'm talking about steel. So now, when it was thought that if we look at the radius of the hydrogen atom and the chlorine atom. Now, here's the other thing too. When we talked about ionic compounds, we talked about ionic radiuses, okay? And the electrostatic attraction between the two. When we talk covalent compounds, there are no ions here, okay? So we're talking about the radius of the element, the hydrogen atom and the chlorine atom. Now, the hydrogen atom has a specific radius given there by R1, which is has a diameter of 0.073 nm. Nm is like centimeters and meters. N is nanometers here. Okay, you ever heard of nanobytes? We're talking about down, when we hear the prefix nano, we're down at the atomic scale. Okay, so hydrogen atom has a diameter of roughly 0.037 nanometers, and the chlorine atom has 0.099 nanometers, very tiny. It was thought that when these two atoms got together, that the new bond length that they created would have a length of 0.127 nanometers, which is basically the sum of those two numbers, okay? However, it turns out that that's not the case. This is the sum, excuse me, I gave you the wrong number. The 0.136 nanometers, change the color of that. This one right here in yellow is the sum of the two radii of the hydrogen atom and the chlorine atom, okay? And so it was thought when the hydrogen atom and the chlorine atom come together, that would be the bond length, the length of that bond, and that would be 0.136 nanometers. In reality, it turns out to be 0.127. And so what's happening is there is an area of overlap. Okay, an area of overlap denoted right in this particular region right there. Oh, let me clear this up here a little bit. Right here, this area of overlap right here. And so the result is that the electrons coming in from the hydrogen, the valence electrons coming in from the chlorine atom, they come together. The hydrogen has 1, the chloride has 7, and guess what? They come together and form a bond. I could draw this in this manner. Let me do it like this to see how this bond is formed. And so we know that the chlorine has 1, 2, 3, 4, 5, 6, and 7 valence electrons. Those are these dots I put around. I'm getting a bad connection. Okay. And we know that the hydrogen has a 1 electron on the valence shell. Guess what? Look at this. When they come together, these two, one coming from the hydrogen, one coming from the chloride, come together to form this bond between the hydrogen and the chloride to form a single bond. Okay. The octet has been fulfilled. In the case of the ionic bonds where the octet was fulfilled by losing or gaining electrons, when it comes to covalent bonds, when atoms come